Hi, welcome back to Calculus. Today we're looking at section 7.1 in our book, the logarithm defined as an integral. So it turns out there's this really fun connection between natural logs and integrals of this, and we'll talk about it in just a second. And so that's what we're going to be exploring today, is this idea of defining a natural log as an integration problem instead of the inverse of an exponential function. All right, anyway, so here we go. The definition of a natural logarithm is that the natural log of x is equal to the integral from 1 to x of 1 over t dt, where x has to be greater than 0. Which makes sense given how we have defined natural log in the past as the inverse of an exponential function. You certainly can't be plugging negative numbers into a natural log. And so we have a couple of things to look at here. If x is less than 1, so still bigger than 0, but less than 1, then we get a negative value out of that integral. And all you'd have to do would be to kind of look at the graph of 1 over t to start to get that idea. Oh, well, actually, and it's really because if x is less than 1 and put together with what that graph does look like, you're going to be doing an integral backwards. If x is equal to 1, we get 0. If x is greater than 1, we get a positive value. And we have a definition then for e. E is the number in the domain of the natural log of x that satisfies the natural log of e is equal to the integral from 1 to e of 1 over t dt, and that's all equal to 1. So this all fits together with what we know about natural logs. We know that the natural log of e should be 1, and yeah, it's kind of fun. So let's move on and take a look at derivatives of these. All right, so let's continue on. Let's look at derivatives for natural log. So the derivative of natural log, we're going to use the first part of the fundamental theorem of calculus, is equal to the derivative of this integral from 1 to x of 1 of t dt. But if we remember our fundamental theorem of calculus, that just ends up equaling then 1 over x. And so the derivative of natural log is 1 over x. Which means we can expand that just a little bit and have a differentiable function inside of our natural log instead of just an x. And so the derivative of the natural log of u is 1 over u times du, where u is greater than 0. And u is a differentiable function of x. And that's something that we get by using the chain rule. And one last step here, two more, I guess. The derivative of the natural log of the absolute value of x is 1 over x, as long as x is not 0. And finally, the derivative of the natural log of b times x. So we have a constant inside there with the x. So this is kind of a fun little outcome of natural logs and their derivatives. So the derivative of natural log is 1 over what's on the inside. So in this case, 1 over b times x. But because we have to do that chain rule, we're multiplying by the derivative of b times x, which is just b. So I have 1 over bx times b. The b's cancel out, and we just get 1 over x. So even having a constant inside of your natural log doesn't actually change the derivative, which is kind of weird. So let's get into a little bit more. We're going to have some integration. Okay, so let's finish up looking at this section with natural logs. Let's do some integration. We have that the integral of 1 over u du is the natural log of the absolute value of u. Now we do have to have a positive value that goes inside our natural log. So we do need that absolute value just in case u is negative. So it turns out then that means that the indefinite integral, there we go, I can talk, of f prime of x over f of x dx is equal to the natural log of the absolute value of f of x plus c. And that's basically because we're doing a substitution. If we have a function on the bottom, we can call it u. Its derivative then, well, let's look at the example. That makes it all look pretty nice. So I want to evaluate this integral from negative pi to 0 of 4 sine x over 7 plus 2 cosine x dx. So I called u the bottom, 7 plus 2 cosine x. Du then is negative 2 sine x dx. I divided both sides by negative 2, so that I have negative half du is sine x dx. So in place of the sine x dx that I have here, I put the negative 1/2 and my du. So I still have the 4. I didn't lose that. And cleaning that up, then negative half times 4 gives me negative 2 over u du. Now, the 5 and 9, those are what you get if you plug in negative pi and 0 into the inside of this mess, right? We're changing to u, so we need to change the limits of our integration. Go back and check that, make sure I did that right. Pretty sure I did, but you never know. So now we're integrating this from 5 to 9 of negative 2 over u du. That is negative 2 times the natural log of that absolute value of u from 5 to 9. We plug it in, negative 2 natural log of 9 minus negative 2 natural log of 5, which makes this positive, so I put it in front, 2 natural log of 5 minus 2 natural log of 9. And then I just use some basic rules for logarithms, and I've factored out the 2 and combined my 2 logs into 5/9, because that's what happens when we have subtraction with logs, they become fractions. So there we go. There's our answer, and there is section 7.1. Have a great day.